I'm Eran, and I'm here to talk about real-time deep learning inference on video feeds. Before I do that, a little bit about where I come from. I work at Advanced Analytics Department at Intel. We're composed of approximately 160, 170 personnel from data scientists, project managers, and software developers. And we do a lot of projects and supply solutions, or implement solutions rather, and products for different divisions at Intel, from the manufacturing through design and sales and marketing. We even have some products that are deployed outside of the company. Such one product is to support collecting sensoric data for Parkinson research. But today I want to talk to you about a solution we recently deployed in order to help Intel in its testing or QA process. We're trying to automate visual inspections. What does that mean? Through the manufacturing process, Intel chipsets go through a rigid QA process. One of them are stations at testing labs, which personnel look at screens showing films and video games. Seriously, that's their job, looking at those screens and identifying defects on the monitors. Let's say a black spot or a distortion of the image, and some other defects and anomalies. We're requested to replace those personnel or assist them by placing video cameras, looking at those screens, identifying those same defects and maybe even more that a human would not be able to detect, in order to verify the chipset in the manufacturing process. And I dove right in because I have only 15 minutes, so I'm sorry if I'm doing that too fast. So after examining this use case, we came to realize that visual inspections are a bit different than video understanding when you're trying to do video analysis. Because in our use case, first of all, when a human looks at the screen, he can identify many defects that come from very different worlds of knowledge. And we assume that these worlds of knowledge would require many different deep learning models. And in fact, that's what happened in practice. And we have, for a single process, we have approximately 10 or 11 deep learning models that need to be analyzed in order to identify the defects of a single frame. The second thing is, well, you can assume some kind of smoothness when you want to understand what's going on in the video, meaning if you have identified a vehicle, it will still be a vehicle in a millisecond or 10 milliseconds. You cannot take this assumption when you're trying to do anomaly detections or detect defects that may be short-termed. So you need to scan each and every one of the frames, and you cannot downscale the frame. So we did receive 30 frames per second and analyzed each one of the frames in order to identify those defects. As you can understand, these problems are quite unique, so the research is not big on them, such as research you can find on object detections and other video understanding algorithms. And the last thing is, the only thing we could do is place video cameras. We could not place like edge hardware, only video feeds that would be sent to us in order to analyze them and identify the defects in as close to near real time as possible, because they wanted this specific testing lab to react as a human would. After examining this, we have decided to develop a framework that would centrally serve deep learning models with focus on low latency. And I put emphasis on low latency because most of the efforts that you see today is get the highest throughput possible. But we do care about throughput, but mostly about getting the lowest latency possible from the inference. And not just for a single frame, like the first frame or the second frame, but for each one of the frames, constant lowest latency over time for the entire video feed. So if we look at the illustration of one of the POCs we did, today we have a lot more models, but let's say we have video cameras across the lab, and they're capturing frames that are approximately together 100 frames per second. And each one of those frames would go through 3 CNNs, 2 LSTM, and then there's a reasoning process that would ensemble those results, detecting the final result, or if the frame is deemed defected, or is it okay. And we were able to run this POC and do this in less than a second inference time. Of course, it depends on the models, but in general, these are the times that we're talking about. And we're able to do that by using the lowest possible inference time for each one of those models. And this is key, as we're going to see in the architecture. And I haven't mentioned that, but I'm not going to talk about the models. This is sort of a software engineering lecture, and I'm going to give a few architectural principles that we followed in order to get this low latency. This didn't come without challenges. I believe you're all familiar with the challenges of inference in deep neural networks, specifically CNNs. They are hard, a lot of computational effort. It takes time, and we're expected for fast turnaround and react in near real time. And if you're thinking about batching in order to get better vectorization and prioritization of those computation of the forward pass, then batching, waiting for a batch to fill up, actually hurts your latency, so that's counterproductive. We do use the batching mechanism, but a little bit differently in order to get low latency. And as I mentioned before, we have a variety of models, so we need to do everything fast, and we need it to go through many different models, not just one, and have a reasoning process ensembling all those results into the final result. So without any further ado, internally we call it Archelon. It's a framework, actually an asynchronous framework that supports real-time deep learning. It's fully automated and fault-tolerant and scalable framework. And in high level, this is the architecture. It's very simple. It's divided into 4 main components. We have the API, the data store, it's easier here, the application, and the model. And the critical path, that's the main issue, now became very simple. It's down there. There's nothing magical happening over there. You simply need to save the frames. First, save the frames. So the API gets the frames, and you save them into the data store. If you want a result, you pull them from the data store through the API to the end user. Now, the upper part is where the magic happens, so to speak. This is an asynchronous system. So you have the application, which pulls the frames for processing, and you have the model part, which helps them get the inference. You can think about the application part as a collection of Python processes, so asynchronous Python processes, and we're going to deep dive into that part because that's the most special part in the system. And you can think about the model as a collection of microservices, which you probably experience yourself when you set a service specifically to serve and get inference for a specific deep learning model. So the main component is the application, a collection of asynchronous Python processes. They're actually the basic building block of the system are many asynchronous inference units, or AIU as we call them, which their entire role in life is getting the fastest inference possible from this, let's say, deep learning microservice. The AIU is an always on, always working, always using the resources processing unit. It looks into the data store, finds whatever frames is waiting to be processed, pulls them out, does some pre-processing specifically for that TensorFlow model, send it for inference, get the result, does some post-processing, and save the intermediate result, let's call them, back to the data store. Now, while it was working, some other frames, because this is a real-time system and the video feeds keep on coming, some other frames got aggregated inside. So it pulls whatever got aggregated inside and does the same thing over and over again. As you can understand, this creates this phenomena of dynamic batching, let's say. We do not have a constant batch size, but this dynamic batching soon, like after 1, 2, 3 cycles, converges into a constant batch that is optimal in order to get the fastest inference rate for that specific model, or the lowest latency. The AIU is also, and this is also important, is stateless, which by nature makes it extremely fault-tolerant and scalable, meaning if it needs help, you can simply deploy another AIU that does the same thing, looking at the same queue, and you'll get better performance up until you reach your resources boundaries. Additional benefits are extremely good separation of concern, meaning you can deploy an AIU, and you should deploy an AIU for each one of the deep learning models. And each one will converge to its specific batch size, which will give you the lowest latency possible. Another benefit is we can use the batching mechanism, and since the AIU is agnostic to where the frames came from, you can batch together multiple video feeds into a batch and get lower latency and better resource utilization by using this batching mechanism across video feeds. Because this is a central system, you send all the feed to the same system. And if we look at a high level of how the data flows works, let's assume we have 3 models, one LSTM, object detection, and a ResNet. We want to deploy those 3 for fast inference. Then we deploy 3 AIUs or more, but each AIU is designed to work with that specific deep learning model. And each will converge to the best batch size. And after all these intermediate results for each deep learning model will be saved, there is a reasoning process, which is also asynchronous, similar to the AIU, but it does not do any inference. It simply takes all those intermediate results for each one of the frames and does the reasoning, the ensembling of the final results. As you can see here, the second model have detected a defect, and the reasoning process have deemed this frame defected to be saved to the data store, so the end user will see that this frame has an anomaly or defect in it. To conclude, I want to give a few, let's say, general suggestions on how to reduce latency, which we learned along the way. That are quite trivial, but important to remember. First of all, most models do not work. You do not need high-resolution image. So if you can receive smaller resolution or lower resolution images, rather, then do that. If you cannot, then resize the image on arrival and save it in the highest resolution you need, which is usually not that high. You do not want to carry around a huge image with you. It costs in time. The second thing, separate your presentation from your prediction. If you do not need the presentation, then only carry around what you need. At the end, you can attach your prediction to the presentation at the data store. And this only works if you work in asynchronously and you have shared storage, which all the units share among themselves. Choose your processing resources according to need. Not everything works best on GPU. I work at Intel, so I'm obligated to say so. No, I'm just kidding. But we found that some models, mainly LSTMs, worked for us better on CPUs. So test which hardware gives you the best performance and use that. And the last thing, which is related, use the best serving method. If you're training a model using TensorFlow, please serve it using TensorFlow serving, because you will get the best performance other than writing something in-house. So this was our architecture, and this is how we got really fast or low latency when inferencing deep learning models. And I was Eran, and I think I'm done.